It's great to be here. My name is Engelberg. I'm a research associate principal at Accenture Cybersecurity Labs, located at Israel. Our research is engaged with applied AI and other cool semantic technologies around the domain of cybersecurity. Today I will be speaking about adversarial risk analysis over critical missions within the company. First I will talk about the challenges, then I will demonstrate what is the proposed approach, and the whole demonstration will be around a vehicle assembly use case. We will deep dive into attack graphs and then how we do quantify the risk over the infrastructure layer and how we propagate it to the business layer. And then I will present how we do risk mitigation plan, how we use knowledge graphs to prioritize which issues to fix first. And finally, I will demonstrate a very cool capability of the approach with what-if analysis. Stay tuned for it. Okay, so we've seen in the recent years that there is a clear trend of digital transformation and smart manufacturing, and that this trend increased the risk over manufacturers. Current tools in the industry prioritize risk based on infrastructure criticality. And we claim that there is a need to prioritize the risk according to the business, not according to issues within the infrastructure alone, but whether these issues affecting the business, the core business of the company. But this arises few challenges. First, how do we quantify the risk over the infrastructure level? The second challenge is how do we map the risk from the infrastructure level towards the business level? And finally, how can we prioritize the issue fixing according to business importance? So these are the challenges. And before I deep dive into the technical stuff of the presentation, why are we using graphs? So first of all, this is a Graph Connect conference. So this is the reason that we're using graph. But actually, we use graph because it creates full contextual view of the challenge. We are able to model the adversary behavior within the system using graphs. We are able to model the adversary effect over cyber assets, and then to model the different dependencies between cyber assets to business processes or business activities within the infrastructure. And finally, we are able to model using graphs the dependencies between industrial processes and between different steps within the process. Okay? So this is our approach in a nutshell. We first collect security findings within the system. These are findings such as that a device has an internet connection or the device has malware, etc. And we use inference rules that were modeled by cybersecurity experts. And then we use inference engine that takes all of this information and create an analytical attack graph. Based on this attack graph, which simulates the potential adversary behavior within the system, we take the potential adversary behavior within the system and we connect it to the business layer using information about business to asset mapping. Okay? We call this representation a process-aware attack graph. This is actually kind of a digital twin of the industrial manufacturing process. Okay, includes its infrastructure. Then, based on this representation, based on this knowledge graph representation, we do all of this cool stuff on the right. First, we quantify the risk within the system when we propagate it to the business layer. Afterwards, we create risk mitigation plan, how to reduce the risk according to the business importance. And lastly, we are able to use the whole approach, the whole methodology, the whole framework, in order to do what-if analysis. In what-if analysis, we are able to simulate theoretical exploits to the system and to see what are their effects, how they affect the business, how they affect the risk, etc. This work was part of a collaboration with a startup company which called Otorio, and of course with Accenture Security. And of course that we use Neo4j behind the scenes and GDS. Okay, so before we deep dive into the process-aware attack graphs and how we calculate the risk, this is the showcase of this demonstration. We are talking about vehicle assembly process flow. The graph here is graph of business activities. You can see here each node is a business activity, is a step within the process. We can call it a process element. Okay, nodes that are marked with blue represent steps or process elements which are not at risk. Nodes which marked with red represents process elements which are at risk. Okay, and nodes which are marked with gray represents nodes that we do not cover their infrastructure layer. This could be because the collector is not collecting data from the infrastructure. This could be, in some cases, that this step is manual, okay? And we don't have coverage on any infrastructure layer in terms of this activity. Okay, relations in this graph represents the fact that one process element is directly followed by another one, okay? In that case, you can see here that door disassembly comes before dashboard installation and door module assembly, and so on. Okay, so now let's talk about process-aware attack graphs. First of all, the first layer of the process-aware attack graph is the analytical attack graph, which simulates the potential lateral movement of the attacker within the system. This graph has three types of nodes. Facts, which stand for evidences that were collected within the system. Impact, which stands for new capability that the attacker gains during the attack. Rule, which stands for the attack technique that's being applied by the attacker during the attack. Okay? Attack goal stands for an impact, which is a predefined attack goal, a predefined capability that the attacker gains within the system, which saying that he reached the goal of the attack. And entry point stands for a fact that is defined as an entrance point into the system, of the attacker into the system. There are two very important features of the graph. One of them is the hardness category, which is an attribute of the rule, of the technique. This attribute stands for the required maturity level of the attacker to perform the attack, to perform the concrete tactic. Okay? This category starts from inherited technique and ends with nation-sponsored techniques, and it's correlated to a score. As long as the score is higher, it means that the technique is more difficult to perform. The second attribute belongs to the impact, the attack goal. And this is the impact vector. Impact vector is a vector of severity of the action that the attacker could perform to the system in case that he reach the state of the attack goal. Okay, the severity vector, the impact vector, has four perspectives in terms of availability, integrity, confidentiality, and safety. Okay, so this is an example for an analytical attack graph. You can see here that the attack starts on fact that this device has malware, and then the attacker continue to perform steps within the infrastructure until he reaches these two capabilities. The first one is that he can perform process-aware tag manipulation, and the second one is that he can start or stop the OT device. Okay, you can see here that each rule has different hardness category. and that each attack goal has different severity or impact vector. Then we take this analytical attack graph and we enrich it with information about cyber assets. Okay, we extract from the facts and from the impacts what are the related cyber assets. Okay, and then we use the business to asset mapping to map it between the cyber assets to the business process, to the process elements. You can see here that these two assets has connection to the marriage process. By the way, marriage process, it's not like in real life. It's when during the process you take two parts and you perform marriage to these two parts, and there is no divorce until, okay. There is another type of connection that we talked about before, process dependency connection between different process elements. You can see here that windscreen assembly comes before marriage, and marriage comes before wheel assembly. This will be an important feature to the way that we are propagating the risk, and you will see it right away. Okay, this is a very cool demonstration or visualization of how we present to our users the process-aware attack graph. You can see here below highlighted the potential adversary behavior for each process element, and that each potential adversary behavior is mapped to the corresponding process element. Okay, this showcase is around a few thousand of nodes. Okay, but we've seen scenarios of 10 millions of nodes and so on. Okay, so after we define the representation of the process-aware attack graph, now I want to show you how we calculate the risk based on it. First of all, risk, we define risk as multiplication of impact and probability. Okay, when impact is the severity that will, the severity of the risk event, and probability is the chances that this risk event will occur. We take the following approach. First, we ask what is the cyber risk per attack goal. Afterwards, we ask what is the cyber risk per cyber asset. We propagate it from the adversary behavior into the asset level. And finally, we ask what is the cyber risk per business process. This is the complete approach in a nutshell, and now I will dive in a little bit further. Let's start with what is the cyber risk per attack goal. You can see here on the right a sample of a process-aware attack graph. These nodes are related to the analytical attack graph. You can see here 3 different types of attack goals, of capabilities that the attacker gains during the attack. You can see here 2 instances of cyber assets and 1 instance of process element. Okay. In one sentence, we want to quantify the risk over the different attack goals based on the easiest way of the attacker to gain this capability. Okay, how we do it? So first, we extract the hardness score as a weight on the outgoing edges. Then we run k shortest path algorithm with k equal to 1. It means this is all shortest path between all entry points within the graph to the ending points, to the attack goals within the analytical attack graph. And we use the hardness score as weights to drive the algorithm. And then we get, for each attack goal, all the easiest ways to reach the attack goal. Okay? Then we take the most easiest way to reach the attack goal according to the minimal cost of the algorithm. Afterwards, we calculate the risk vector for each attack goal as multiplication of the impact vector that you saw before. And we have an impact vector of availability, integrity, safety, and confidentiality with a metric that we call hackability. Hackability is a metric that represents how easy is the attack. as long as the attack is harder, the probability is lower, and vice versa. Okay, and this is the quantification of the cyber risk over the attack goals. Then we want to propagate the risk from the attack goals to the cyber assets. Okay, and we have the same running example. You can see here on the right that there are 3 instances of attack goals, 2 instances of hosts, of cyber assets, and 1 instance of marriage, of process element. The approach that we are taking here is based on a worst case scenario approach. We say that if an attacker reaches the state that he can perform 2 different types of attack goals, we take the worst case scenario that he will perform both. Okay, so we take the maximal risk per aspect. Okay, you can see here that we've taken the availability risk from the can perform tag manipulation attack goal, and the rest are taken from the can stop OT device. Okay, and then we propagate the risk further on to the industrial process using similar approach of maximal risk per aspect. Okay. I will take questions at the end. Okay. Okay, so do you think that we're done? We are not done yet with risk quantification. I think that this is one of the most powerful capabilities of our approach. You can see a scenario that the marriage process and the windscreen assembly has risk because they do have relations to cyber assets. But the question is whether the wheel assembly that you can see here, does it have risk? So of course the answer for this is yes, it has risk. The risk here is indirect risk, okay, which is sourced by the risk of both the windscreen assembly and the marriage process. If the marriage process will stop, it means that the wheel assembly process element will stop as well. Okay, so before I deep dive into how we calculate the indirect risk, how we take under consideration the indirect risk, let's do some definitions before. First of all, direct risk is a risk vector that was measured directly over an element and propagate to its component. Indirect risk is an impact of a risk vector from an element to another that both of them has process dependency. Overall risk is a function of the direct risk and the indirect risk over a process element. And finally, we present here a new notion of importance vector. This is a feature of the relation between 2 process elements, which stands for the amount of risk that we want to transform from one process element to another process element. Okay, I can give you an example here in case that there is a risk of denial of service of a single process element. We want to transform only the risk over availability to the next process element. We don't want to transform the risk of confidentiality for the next element. Okay, so we take the following approach in order to analyze what is the overall risk over the process element. Okay, so first we assume that we already calculated the direct risk according to the method that you saw before. And then we go level by level of the graph. And we first calculate what is the indirect risk, which is in case that this is a leaf node, so the indirect risk is 0. In case that it's not a leaf node, the indirect risk is the overall risk of the previous node. And then we calculate the overall risk of the current node according to the maximal risk aspect, given the direct risk and the indirect risk for each node. And we do it level by level. First, we take the overall risk, we multiply it with the importance vector, and you can see here that we transform to the overall risk over the marriage process only the availability risk from the previous one. And again, we can see that there is a risk over the wheel assembly, okay, which is basically the availability risk of the previous process. Okay. Okay, so we talked until now about vectors, about risk vectors. But our clients told us that it's very hard to grasp the notion of vectors. It's very hard to optimize it based on multiple numbers. So we decided that there is a need to create a single metric that will represent the security posture of the business or of the infrastructure. So furthermore, we want to consider what is the user-defined threshold in terms of risk. It could be that in some systems, availability is more important than safety, for instance, or vice versa. So in order to do so, we present this formula. We basically use sigmoid function of the differences between the predicted risk to the risk tolerance. Okay, and we get a single metric. In case that the difference between the predicted risk and the risk tolerance is equal to 0 or less than 0, everything is okay, and the total score will be a half. What happened? Oh, I can continue. In case that the sum of differences between a predicted risk to the risk tolerance will be more than 0, it means that the process is at risk. Okay, and then the sigmoid function will return to us a value that is greater than half. Okay, so what did we see until now? We've seen that we are able to represent the infrastructure layer of industrial process together with the business process of the industrial layer within a process-aware attack graph. And then we are able to quantify the risk to the infrastructure level and then propagate it to the process level and consider multiple types of dependencies between processes. Now, I want to present how we quantify, how do we prioritize which issue to fix first, according to the business importance. Okay, so first of all, this is the approach for risk mitigation. You can see here the same running example on the right. Actually, this graph is a derivation graph. If we remove a fact, we will eliminate all of the related attack path of this fact. Okay, so we can treat facts within this graph as issues that could be fixed. Actually, facts are the risk root cause in this example. And for example, if you want to remove the denial of service risk from this host, all we need to do is to fix these two facts, and then we will eliminate the all related attack paths. Okay? So the question is, how can we prioritize issue fixing according to process importance? This is the algorithm to do it. Okay? This algorithm gets a process-aware attack graph as an input. It gets the process name that we want, the process element name that we want to minimize the risk for it. It gets the risk tolerance. I think that there is some cyber issues here.
Yeah, I think the AV system needs to work.
Okay. No problem. Okay. Sorry. Okay, so it takes the risk tolerance that the user defined. Okay, the algorithm takes risk score type, that this is the objective of the minimization. Okay, we can minimize the risk according to the total score. You remember before the sigmoid function and all of that. And we can minimize the risk according to a single perspective. For example, only based on availability. Okay, and there is, Now I didn't step on nothing. Okay, great. And finally, the algorithm gets list of facts that could not be repaired based on business requirements. For example, we want that this device will be connected to internet. We cannot disconnect it from the internet. Okay? So the algorithm goes like this. First, we calculate the process risk according to the methodology that you saw before. Then we retrieve the threshold. In case that we decided that we want to minimize the risk according to the total score, we will take a threshold of a half. And in case that we want to minimize according to a single risk aspect, we will take the risk tolerance, the aspect of this risk tolerance. And we take an iterative approach as long as the process risk is greater than the threshold. First, we do a greedy risk loss. We go fact by fact and we calculate for each fact what is the residual risk in case that it will be eliminated. Okay? And then, I will continue. And then after we calculated it, we reduce the fact with the maximal risk loss. Okay, we append it to a list of the mitigation priority, and then we remove this fact from the graph and we create a new subgraph, okay, with without these facts and without the corresponding attack paths, of course. Okay, and then we calculate the risk again and so on until we reach a steady state. Okay, and then finally we return the order of issues to be fixed according to the business importance. Okay, this is an example of the output of this algorithm. You can see here that for the door disassembly process element, there are 3 steps of mitigation. And on the first step, we reduce the risk from 79% to 78% and so on until we reach 0. Okay? Okay. What if analysis? I promised to you that this is the most powerful stuff here. Okay, so imagine that we can use this digital twin to simulate what will happen to our system in case that a theoretical thing will happen, okay? Imagine that I have a factory and there is a very critical device that could control my process, and I want to simulate what will happen if this device will be affected. Okay, do you remember the incident of Log4j that was a few months before? Imagine that I will be able to simulate what will happen to my system in case that I will use Log4j, or similar exploit to Log4j will occur within my system. Okay, we can do it using our approach. These nodes on the bottom are the system nodes, okay, are the analytical attack graph of the system according to evidences, facts that we discovered by monitoring our system, okay? We are able, using our approach, to inject a theoretical fact into the processor attack graph. And then, using the reasoning system, all of the I hope that you edit it afterwards. And then based on the reasoning system, we infer what are the theoretical attack paths on the system and what is the theoretical attack goal of the system. Okay, and then we are able to estimate what will be the risk in case that this theoretical exploit will occur. And more important, we are able to create a mitigation plan based on the current state of the system that will secure the system from this exploit. Okay? And this is a nice demonstration of how we do it. We simulated accessible web vulnerability on these machines. on this machine, and the attack graph was increased by 4 new attack paths. These attack paths affect the marriage process. You can see here a new asset that was discovered as risky within this process. Okay? And now we start with the risk mitigation algorithm. Do you remember that we have in the risk mitigation algorithm a list of facts that we cannot repair? So we use this feature and we inject into this list the theoretical exploit. Okay? We don't want to recommend the user to fix a theoretical exploit because it's pretty trivial and it's wrong. Okay? And then we start simulating the mitigation. You can see here that we fixed, if we will fix this issue of internet access to this machine, we will reduce the risk from 82% to 55%. Next, we will fix these 2 issues and will reduce the risk to 54%. And lastly, we will fix this issue and the risk will be reduced to 0. Okay, and because this is a connected graph, we actually reduce the whole risk within the system. Okay. Right in time. Okay, so the key takeaways from this presentation is first, that we can use process-aware attack graphs to perform risk assessment and a process-oriented risk assessment. The second key takeaway is that we can use graph data science, GDS, to quantify the risk over the infrastructure level and propagate it to the business level. And then we can use, again, GDS for risk root cause analysis and to provide recommendations. And finally, we can use the whole approach to perform a very powerful what-if analysis. And that's it. Thank you.